Now, why do we need to prove? I got this all from your book, so it's easier for you to also read on your own, okay? To convince, you want to convince people that you are sure of what you're saying. You don't want to just base it on, I'm not so sure. You want to tell us you are certain, to convince somebody, to understand, to communicate, to organize, and most importantly, to discover new concepts in maths. When somebody establishes a proof, look at the story that I just told you about the Millennium Prize problem. Based on somebody's proof, a new concept was used to even prove a major word problem. Okay? Now, you'll be, as time goes on, we're going to be needing a lot of this. Some of you in the coding club must have been using some of these connectives directly or indirectly. And, not, and, or, and not. Do you remember this in Python? Yeah, especially. And these are the symbols. If you see this, these are the symbols. I take them one after the other. We call this conjunction, this is disjunction, and this is negation. This is the symbol that I'm used to. But there's a new symbol in your book. It goes like this. This is if then, we call it implication. And this is equivalence if and only if. I'll try to tell you the difference between them. For example, I put an example here, so I'll be sharing this with you also. This simply means A and B, nothing more. Statement A and statement B. So by the example that I wrote on the board, if A means all the boys are playful, and B means all the girls are playful. So when you write this, you're simply saying all the boys are playful and all the girls are playful. Does it make sense? But if you use the other one, that is or, in the case of and, if both this conjunction, can we say this? This conjunction will be true only if both statements are true. Do you understand what that means? Look at this. A is 2 greater than 3, and B is 5 greater than 1. A conjunction B. What is the truth value of this? False. Because what this means is 2 is greater than 3 and 5 is greater than 1. Is that true? Because one of them is false. Okay? Because one of them is false. Do you understand what I mean? But if both are false, what do you think happens? Let's say 3 greater than 1 and Q is minus 1 less than 0, P conjunction Q. What is the truth value of that? Are you sure? Both are false. Are you saying we're going to get true?
Both are false?
Oh, did I say both are true?
Yeah.
Oh, mistake. Okay. For both are true, do we have true here?
Yes.
Do we have true here? Okay, let's check. Is this false? Is this false? What is the truth value of this? Are you sure? 3 less than 1 and minus 1 equals 0. Is this true or false? False. I'm just trying to trick you. You are right. I need you to be sure. I need you to convince me. Okay? So, conjunction will always be true if the component statements are true. If one of them is false or both of them are false, the entire statement is false. Unlike when you have disjunction. If this is true and this is false, what do you say about this? Are you sure? True of us? No, we can't have two.
Only one of them needs to be true.
Only one of them needs to be true to get a truth value T here. So if you have P to be 3 less than 1, which is wrong, and this is minus 1 less than 0, which is true, and the statement here will be 3 is less than 1 or minus 1 is less than 0. Of course, that's true. Because statements say or, not both. Just one is needed. What if both are true? Leo is a member of this class, or Damien is no longer a member of this class. Is that statement true? Yes. Okay? You want to walk around? But if you have both to be false, what do you notice about this? You sure? If both are false? You sure about that?
Okay.
So for this, it will only be false if both are false. But for conjunction, it will only be true if both are true. It's like the opposite extreme end. Negation is just the opposite of a statement. If the statement is Karen is very quiet, the negation is Karen is very loud. Kind of. Or Karen is not quiet. Don't get me wrong. Do you understand that? So if A is a statement and the truth value of A is T, what can you say about the truth value of negation A? Are you sure? Because if the statement is true, opposite of the statement, you'll be false.
Yeah.
It makes sense. Okay? And the last two, if then, now these are the two important ones. If then, this is implication. Implication is what this proof is about. The first step implies the second step, implies the third step. Now, like I said, if root 2, suppose root 2 is rational. What do we call this line again? That line that I wrote, what is it called? I told you a proof has three parts. Something, something, something. Hypothesis. Suppose it is true, then root 2 will be A over B, right? Then we say this implies that 2 equals A squared divided by B squared. We're saying the implication of this statement is this. We are saying if this line is true, then this line must be true. The other way around may not be the case. Okay? You might have something like, I'm trying to see where you can have, okay, if A equals maybe 50, maybe 30 degree, cos A will be root 3 over 2. But if cos A is 3 over 2, that will also implies this one. Okay, then that's not the one I'm looking for. I'm looking for something where one implies the other, but the other one does not imply it. Okay, let's see. Let's see, factorial, I wanted to use factorial. Okay, if A factorial equals 1, then my A will either be 1 or 0, right? And 0 factorial or 1 factorial will also be that. Okay, let's look at negatives. Minus 2 squared is equal to 4. The square root of 4 can also be minus 2. Okay, I'll think of an example where one implies the other, but the reverse is not the case. Okay? That's so because it's not always the case. But in the case where you have it both ways, we say it is equivalent. So if in a mathematical proof, you are asked to prove that statement A and statement B are equivalent, it means A implies B, B also implies A. Do you understand that? So when working through a proof, we use implication. This will imply that A squared equals what? 2B squared. Do you agree? Actually, what this means is that whatever this is times 2 makes it even, right? Right? So what this means is that A squared is even. Do you agree? Twice of something. is even, right? So if a squared is even, what does that tell us? It means our a squared, okay, let's see. But do we know anything about whether b is odd or even? A squared will be even because of this times 2, right? Okay, so if we can get something that doesn't make sense from these, then we are fine. If a squared,
You can write that online.
really?
Yeah.
Okay, so what part am I missing?
I think it says like A and B have no common factor or something.
Okay, let's see. If a squared is even, then maybe a squared can be written as some 2m. Yes? If that is the case, then 2m, let me see if this works. Then m will be some b squared. We're going back again.
Wait, can you square both sides again?
Oh, that would be too much. No. We just need something that doesn't make
Then
sense.
you get A plus B.
A plus b. No. We have a 4 here.
Yeah.
Mr. Daniel,
We must have a 4 here.
here, do you want to see that?
Let's see what I'm missing.
It's saying
It's been a
that
long time I did this.
like, both A and B have to have 2 as a common factor.
Oh, okay. So to divide that expression, blah blah blah, a squared is even, which implies that a must be even.
Oh yeah, that's what I'm missing. If a squared is even, you cannot square an odd number and get an even number, right? Do you agree, everyone? So which means a must be even. If a is even, what does that tell us? So a can be written in this form. And if a is written in that form, let's see, we can have 2m squared to be equal to that. That's going back again. 4m squared equals some 2b squared. It means that what happens again? It means 2m squared equals b squared. So b also must be even, which means b is even.
It says on the top A divided by B both have to have no common factor.
Ah, that's true. If you write a fraction of this form, yes, you want to make sure that they are, we call them co-primes. Co-primes are those numbers with just HCF of 1. This is the simplest form of your fraction. Okay, and with this, you can already see that they have something in common. Because if I substitute and I say A is even and B is even, then we can always bring something out. Then we have something that doesn't make sense. If indeed they have nothing in common, if both of them are even, then they still have something in common, which is 2 at least. Do you understand that? From here, A is even. Even when you go further, B is even. If A and B are even, then this is not the simplest form of that fraction. And if you write a number as a rational form, in form of a fraction like that, A and B, one of the assumptions is that A and B are co-primes, which means they don't have anything in common to simplify them. And getting the fact that A and B are even here shows that they still have something in common, which means your first assumption must be wrong. That's the sign of thing I'm trying to show you. We'll do some of these things a lot better when we get to prove by contradiction. Okay? Now, what is the point I'm trying to make here? Equivalence simply means the other both ways are valid. So if A happens, B happens. I'm trying to see an example. A squared equals 4 is actually equivalent to A equals 2. Because if A squared is 4, A is 2. If A is 2, A squared is 4. Do you understand that? So that's equivalent. So we say these two sides are equivalent to each other. And we use if and only if. So when you start maybe some proofs or even at beyond this level, like university, you will be seeing something like proof that the two statements are equivalent. This is what they're expected to do. They're expected to justify in both directions. Okay? Now, let's go into some calculation. Maybe that will help some of us, so we don't sleep in class. I know these parts can be a bit boring. We've talked about negation, okay, implication, we've talked about that. Converse. Converse is opposite of something. Now look at this. The converse of an implication is this. So the converse is like the opposite direction. Okay? In this case, this implies this, the converse is this implies that. So when you have if and only if, it means the converse is also true. Do you understand my point? In the case of implication, the converse may not be true. It could be, but it is not required. Hello? Am I making sense? Converse is like the reverse of that implication. So if your converse is true, then you have an equivalent. That's the point I'm trying to make. Look at this. This is an implication, like we said. The converse will be B implies A. Okay? But the converse is not expected to be true in the first one, in this part. The converse is not expected to be true in this. Not the requirement. We are about the direction here. Oh, the first one implies the second one. That's what we are trying to connect. Okay? When you go the other way around, you have the converse. We don't really need to emphasize on the converse when talking about implication only. But when you're talking about equivalence, you are dealing with the first one, the implication, and the converse as well. Okay? And when the converse also holds, then you say you have an equivalence. Which means A implies B, and also B implies A. So B implies A is the converse of A implies B, the opposite direction, if I may put it that way. Does it make sense? Let me see what I'm missing out here before we move on. I just want to brush through with this equivalence. We're talking about equivalence. Okay, let's analyze these questions together. For each statement, state the negation. What is the negation for the first one, 1A? The cat is not black. 1B. X is not prime. C.
The tree is not deciduous.
That's it.
No, it's not.
It's not. Right? Just use the word not. That's it. State with justification whether each of these statements is true or false. If x squared is 9, then x is 3. Is it true?
Yes.
Is it true? Why?
It could also be -3.
It could also be, but this is still true as well.
So true.
Yes, this is true.
If I put something like x is, maybe the only value is 3, then you can say, oh, that's not true because there's something else, right? If x is 3, then x squared is 9. Is that true? Then x is 3 if and only if x is equal to 9. Is that true?
No.
Yes, no? Which one? If and only if.
No.
That's an example I put here. It's true.
It's true, wait.
Only.
3. If and only.
That should be -3.
X and negative 3 can.
X is 3 if and only if x is equal to 9.
Or if X is
Only.
also negative 3, then it can also be. It can also be.
We are saying, does this imply this?
Yes.
Now, does this imply this?
No.
Yes, it
Yeah.
does.
Yes.
Yes.
So this is true. The if and only if is not telling you that is the only value. It's telling you it's an equivalent
Okay,
statement.
that's all.
Because if you claim that A is correct and B is true, both A and B actually implies that.
Oh,
Does it make sense?
okay.
What about 3A? If x is positive, then square root of x is a real number. That's the simplest way to say it.
But
Is it true?
Real number includes positive and negative.
I don't know. What do you
Does it?
think? If x is positive, then x belongs to R. Is that true?
Wait, what's that?
I could also
No.
be No.
No? Why, Leo? Give me a counter example.
Um,
Pi. If x is pi, square root of pi is what?
it's not. It's not.
Really?
It's still real. It's just
It is.
irrational.
Real is if x is
Square root of pi is not real?
It's real.
You want to check your calculator? If you trust your calculator more than you trust me. That is true. The square root of any positive number is still a real number.
No, but isn't complex numbers supposed
Really? Complex number is positive?
Can complex number have positive and negative?
Wait, listen. What do you mean complex number has positive or negative? Complex number have two parts. You only discuss the positive or negative of the parts, not as a whole.
No, I think you meant what if x is imaginary?
Yeah.
Oh, I see what you mean. No, we don't have that. We don't order complex numbers.
Wait, sorry, what does that mean?
You don't order complex numbers to say, oh, maybe this is greater than that or something like that. So if you don't order, then how do you know which one is positive or negative? So for complex number, we don't deal with positive or negative. You only consider whether their parts are positive or negative. Okay? Look at how do you represent your complex number on that Gann diagram. Is it like a positive negative direction? You consider it like a coordinate, right? So you don't think about, but so when we say x is positive, we're talking about real numbers actually. Okay? So it's true. What about b? If x belongs to, if square root of r, square root of x belongs to r, then x must be positive. If the square root is in r, then x is positive. Is that true?
But
Of
you got
course.
square root negative number.
Because you can only have square roots of square root of negative will only be a complex number, right? So x has to be a complex number to have the square root not in r. Do you understand what I mean?
Yeah.
X has to be negative for the square root not to be in r.
So we don't consider complex numbers here.
No, because there's no reason to consider it yet.
Sorry, what?
There's no reason to consider it yet. If the question had said, let me see how it can be a complex number. If x is negative, then square root of x is in r. Then that will be false. Because if x is a negative, square root of x is a complex number. X could be a real number, but doesn't justify that the square root is a real number. That's the point. She's lost.
R is just I.
If x, listen, if x is in R, you see, if I change, can I have attention please? If I change this to this and this to that, it's a different question. If x is real, can we say the square root of x is, I don't want to use positive. Can we say the square root of x is this? Does this imply this? Are we guaranteed? Why?
Because x can be negative.
That's what I'm trying to tell you. But that's not the situation here. X is already given as positive. A positive real number.
Complex numbers we have negative. Wait, so for complex numbers there's no positive?
No. Does that make sense, everyone? So let's look at, so if this is true and this is true, can we say C is true? Because that is just the combination of both, right? So it means A implies B, B implies A, then A if and only if B. Does that make sense? Let's see. Write the converse of this statement. Yes. What will be the converse of that statement? This is actually a good example that I was looking for.
If Socrates is an animal, then Socrates is a
Yeah, that's the converse. But is the converse true? Is the converse true?
No.
Are you sure? If it's an animal, then it must be a cat. Does it have to be a cat? It could be a dog. According to our biology teacher, it could be a human being. Because we are all animals, right? But not in a negative way.
We're animals.
Does it make sense? So you can see a statement is true, but the converse is not true. Okay? So in this case, you cannot have an equivalent statement. You can only have it one way. That's the kind of a statement I'm trying to look for. Okay? Let's look at this. Relationship following. But that's what I mean by relation. Not like relationship, don't get me wrong. Relation on our Instagram is follow. That's the relation we can establish. We follow each other, right? Let's assume all accounts are public. Okay?
Okay.
That I follow you on Instagram doesn't mean you follow me.
No.
So that is like the converse now. I follow you on Instagram. It could be the if this happens. It's like saying, oh, if I click on that button, then I follow you. Now, does it mean that you follow me back? So in terms of relation, there are other words we use to describe some of these things. So we say a relation could be symmetric. When it is symmetric, it means the other way is also true. For example, being the brother of someone is not symmetric. We can say Lillian is the brother of Mr. Cheng, but we can't say Mr. Cheng. No, we can't say Oh, no. You can say, oh, Lillian is the sister of Ethan, but you can't say Ethan is the sister of Lillian.
Yes.
Right? So, the brother of, as a relation, is not symmetric. But friend of, even friend of may not be. You could call me your friend and I don't see you as a friend.
Ow.
You know? You understand my point? Something like that. Sibling, it will be symmetric. Okay? If A is the sibling of A, then B is also the sibling of do you understand? A is a sibling of B, then B is a sibling of A. So picture this thing like that symmetric relation. Relation is a thing, is a different thing entirely in maths. Okay? But it works just like this. Can we quickly look at, I don't think we'll be able to do the other thing, but let's look at the last one here. Determine whether or not this is equivalent. X, Y, Z equals 0. How do we pronounce that? This is statement A. X, Y, Z equals 0, which means the product is 0. How do you pronounce statement B?
X equals 0 or Y equals 0 or Z equals 0.
Yes. Are these equivalent?
Yes.
Of course. If this happens, then this happens, right? If this happens, it means any of them, just one of them needs to be 0. That's the meaning, right? Then this will also happen. Look at this. Are they equivalent?
No.
Are you sure? X is even, B, X squared is even. Are they equivalent? Let's see. If X is even, is X squared going to be even? Yes, you agree?
Yes.
Okay, let's look at it the other way around. If the square of a number is even, is the number even? All you have to think about is it possible for the square root of an even number to be odd number? Is it possible? We're not talking about half of them. We're talking about the square root now. It's possible you divide 50 by 2, you get 25. Then that's no longer even. But if you find the square root of an even number, you always get an even number, right? Then the two are equivalent. Because going forward, it's true. Coming back is also true. Does it make sense? Then you say the converse is also true. I want you to play around with this yourself later. So I'll quickly introduce to us the last 5 minutes. Please be quiet. I'll just pick one equivalence. The order of my arrangement is different from the order in which it was arranged in your book. This proof, of course, will take us up to January, definitely. Am I picking the last one first? Yeah.